including Busan National University. Also a visiting scholar. He has been and working with as a visiting scholars with Princeton University, MIT, US, Imperial College London. Coming to his honors, also they are very they he is having a lot of honors. For example, Samsung Human Tech Paper Award Silver Prize. He is having several Best Paper Awards. IEEE Comso Asia Pacific Young Research Award. And if I talk about the papers and invited talk, they are also endless, including prestigious IEEE conferences. He play a key role as an editor. Also, he delivered several key talks. That also includes some of the renowned conferences, including Globecom, SmartGate, WCNC, etc. And coming to his publications, so they are very good in number. Also, they are very qualitative. Most of them include transactions, magazines, letters, etc. Also, coming to his research domain, he is working with communication theory, satellite communication, non-terrestrial network, intelligent surfaces, and right now working in so many aspects that those are related to 6G communications. So I mean, he is having a lot of achievements. Those cannot be covered in a couple of minute introduction. So once again, I welcome you, sir. So we are glad to have you as a speaker for this talk. So the stage is all yours for the next one and a half hour. Thank you very much, sir. Once again.
Okay. Yeah, thank you for your kind introduction, Rohit. Also, it's very great honor to participate in this lecture series. So yeah, so let me go to my slide here. Right. So yeah. So hi everyone. Welcome to my lecture. So my name is Wonjae Shin from Korea University. Today I'm gonna talk about rate splitting multiple access, in short RSMA here, and also explaining how we can use RSMA in the context of satellite communications or integrate satellite and terrestrial network.
Before you start, can we have one request, sir?
Say again?
Before you start, can we have one request, sir? Yeah, can we record this session with your permission, if you allow?
Yeah, sure, no problem. Yeah.
Thank you very much, sir. Okay, sir. Please continue.
Oh, okay. Yeah, so let me start my presentation here. So this is what I'm going to talk about today. So first of all, we will start with some key motivation of the satellite communications for the 6G. Then we will move on the technical challenge and the research issue on this satellite communications. So finally, we jump into the robust beam design based on rate splitting multiple access and see how it works in the various satellite communication scenarios. Right, so why do satellite become very essential component for 6G? Before going to details, let me start with some underlying trend of the wireless communication. So since 1980s, the wireless communication system having evolved by increasing user data rate. So specifically, user data rate grows 10 to the 100 times in each generation due to the emergence of the new services. So now we are in between the 4G and 5G. So to supporting upcoming ultra broadband and the massive IoT services, 5G network are expected to offer data rate up to the 100 times faster than current 4G network. So beyond this, the 6G is also envisioned to support even more diverse application with a very diverse requirements. So one of the requirement would be the global service coverage to fill out the coverage whole all of the world. So with this, 6G will realize a hyper-connected society. Right, so here's some supporting data for the coverage imbalance all of the world. So this is a 2G coverage map and 3G and 4G. This is accumulate coverage map all of the world. According to the UN data, 34 of the global populations, which is about 2.6 billion, do not use a mobile internet by 2023. So the situation getting better and better. So it's in 2018, almost half of the global population does not use mobile internet, but now it's almost the 20% of the global population can access the mobile internet. I mean, within a 5 year, but still 2.6 billion people need the internet or connectivity. So in the US here, so despite of the very powerful LTE and 5G terrestrial network, more than 20% of the land and 90% of the earth, the whole earth, including the ocean, remain uncovered by the wireless company. So this, dead zone problem and a coverage problem would be very serious issue in the 6G era. So to fill out the coverage hole or dead zone problem, so use of non-terrestrial network would be very promising solution. So this is one in the sky or in the space will have a much wider beam coverage. For example, in terrestrial networks, it's on the rooftop or something like in just the height of the 50 meter. But when it comes to the high altitude platform system, in short HAPS system, the altitude of this is 20 kilometer. And the LEO satellite, low Earth orbit, is the altitude is about 600 kilometer, and then GEO cases it's about at the height of the 36,000 kilometer. So it should have a much wider coverage. So it can enable extend coverage above and beyond, right? So that's a motivation of the non-terrestrial network. So, but here, in this talk, we just focus on the satellite communications. So let's talk about the roles of the satellite in the 5G and beyond. So there are three different the key applications. The first one would be the extended coverage. So it can provide a data service in unserved area that cannot be covered by terrestrial cellular and underserved area. So the service ubiquity would be the very important purpose of the satellite. And second one is to improve the user experience. So it can reinforce the 6G service reliability by providing service continuity for like M2M or IoT devices or onboard moving platform, including the urban air mobility and the high-speed train or in-flight network and so on. So this is about the service reliability. And last one, but not the least, the also role of the satellites is the multicast and broadcast. Because it has a very wide coverage, so it enables 6G network scalability for the data delivery toward the network edge or even the user terminal. So this is about the service scalability. So those are the key roles of the satellites for the 6G. So here is some more use cases for satellite communication for 5G and beyond. So it's not, the application are not in only the rural area or remote area. Also, it includes some application in the urban area. For example, in IoT connectivity or the broadcasting popular contents or the fixed network backhaul here. So it also disaster relief also would be very important the application for the satellite things. As well as some coverage extension in the rural area or the remote area things here. So here is some key terminology for satellite communication. So satellite communication is typically composed of the three components, right? So gateway and satellite and user terminal here. So the feeder link here to connect the gateway with a satellite, whereas the user link to connect the satellite with a user terminal here. So concatenation of the feeder link and the user link is called the forward link, and while the reverse link is called the return link. So in typical the terrestrial network, it has only the downlink and uplink in between base station and user terminal. But when it comes to satellite communication, it's like more like a multi-hop problem. So it has the first hop would be some like the link between gateway and satellite. The second link is the link between satellite and the user terminal, right? So let's keep that terminology in mind. And then let's move on to satellite frequency here. So due to the shortage of the satellite communication spectrum, the satellite from conventional the C band or S band here to the Ku or Ka band. It's a millimeter wave band, which offer very greater signal bandwidth than the C band or S band here, right? So however, the Ka band system are much susceptible to adverse weather condition than the existing the S band and C band. So we need to have more like a very powerful beamforming technique, right? Yeah, because on the other hand, so moving to the higher bandwidth allow the smaller antenna size. Those promoting the use of the multiple antenna system, like a beamforming technique. But still, we have a lot of the frequency congestion because these days a lot of the satellite has been launched these days. So many the industry, satellite industry, want to move to even higher bandwidth, like an E band. So Starlink also considering the E band for the feeder link of its satellite connection, because usually the feeder link are very stable. In this case, the feeder link are the link between gateway and the satellite. So the compared to the user link, this link are very stable and yeah. So we can have a more like sharp beamforming, like a pencil beamforming. So yeah, so we can combat very much the path loss due to the higher frequency band. Okay, and then this is a paradigm shift for the uses of the satellite. So typically, regular fixed satellite services cover very large area of the coverage on the ground. So this architecture is set for broadcast, message, or the TV purpose, right? But on the other hand, we are talking about a communication purpose. So this is called a high throughput satellite. They receive a lot of attention these days. So satellite forms a multiple narrow spot beam here. So each spot beam or circle here is formed by the beam or satellite, right? So and there are multiple spot beam here. So each spot beam serve more than one user simultaneously. So if you use aggressive frequency reach across a multiple spot beam, you have higher level interference due to the side lobe of the beam, right? Because as we learn in the terrestrial networks, the beams are not very sharply decayed its propagation, right? So it has a lot of the higher level beam interference here when it comes to the multi-beam transmission. And there are different types of satellite according to the altitude of the operating satellite. So we can classify the satellite into three different classes. The first one would be the GEO, that with a satellite altitude is about 36,000 kilometers. and then MEO, the medium Earth orbit, is in between. And LEO is the LEO satellite is about the 300 to the 1500 kilometer altitude, right? So GEO is very stationary in relation to the Earth. So the orbital period is 24-hour, just like Earth. Okay. So the LEO case is it's very close to the Earth, and it's also it takes only the 30 minutes for its round trip for the rotation of the Earth, right? So it's the speed of the LEO satellite is about 7.5 kilometer per second. So it's about 27,000 kilometer per hour. So it's 7 times faster than the bullet, the speed. So it's a quite fast movement. So it also causes a lot of the Doppler effect and a lot of the routing problem and so on. Okay? So here is the graph is about satellite coverage according to altitude. So if you look at the left axis with the blue curve, so we can calculate how much satellite coverage for a single satellite according to different altitude. Of course, if you are far from the ground, satellite, the beam coverage should be wider. 36,000 kilometer like a GEO range that can cover 33% of its whole the Earth. So in conclusion, if you install the 3 GEO, then you can cover the whole global coverage, right? But when it comes to the LEO LEO satellite cases, it covers only the 5 to the 10% of its whole the global area. But we have to consider the latency because when it comes to the distance between the satellite and the user terminal, it has a lot of very longer distance compared to terrestrial network. But latency is depending on the altitude directly, so it's a linearly proportional. But according to VoIP, companies such as the Cisco, like 150 millisecond is normal latency for the VoIP, the phone system. So this means that, okay, so when you speak into the phone, it should not take longer than 150 milliseconds for the end user to hear you, right? So we have some strict constraint. Yeah, right. I mean, if you want to support like a 4G-like communications, 150 milliseconds should be the largest latency. Then you can conclude that only the LEO satellite can support this 4G-like LEO satellite for the 6G system, right? So GEO cannot support such the VoIP system because it has a very long latency. So like a 0.5 second is, I mean, it takes a 0.5 second for the round trip delay if you use a GEO system. So you can experience some very large delay when it comes to GEO. So those are the reasons why we are become a big fan of LEO satellite these days. Okay. So those are the pros and cons of the LEO satellite system. So here's some pros. So the first advantage is lower latency. As mentioned earlier, so it can provide 4G-like, LTE-like latency requirement, such as like 2 to the 5th million. And also it can save a lot of transmit power. I mean, compared to the GEO with a 36,000 kilometer, I mean, away from the ground. So LEO satellite the altitude is only 600 kilometers, so it can save a lot of the transmit power. And then also it might have a very small size of satellite. So this is actually the SpaceX rocket, which is the name is the Falcon 9. So it's launched the 60 aerial satellite at one time, because it contains lots of it contains like about the 60 LEO satellite at the same time, and it's launched on the space. And also they develop some kind of reusable rockets. So as you see here, the rockets are after launching the LEO satellite, and the rocket is come back to its ground, and they reuse more than 10 times launching cost. But there are some technical challenges. So the first one, very limited coverage compared to GEO. So it requires massive satellite because it covers very small coverage. So it requires so many LEO satellites for supporting the global coverage, and also short visual time. So it's very so as I mentioned earlier, it's the speed of a LEO satellite is 7.5 kilometer per second, which is correspond to 27,000 kilometers per hour. So it's very quickly far away, and it's not visible within within 10 minutes. It's gone. Yeah. So it's very it has to launch lots of or massive constellation of the LEO satellite for global coverage. And also due to the very fast movement of the LEO satellite, it also like a 45 kilohertz at S-band, like 2 gigahertz at 600 kilometer altitude. So it's almost the 50 times higher Doppler shift than 5G supporting Doppler shift. Okay. So that's a technical challenge for the LEO satellite. So many LEO satellite communication operators already start to launch their satellite to form a massive constellation. So with a target of 42,000 satellites, SpaceX, it's from the US, they already start launching in 2019. So now, as of the April 2024, it's already almost 5,000 aerial satellite has been launched. So you can imagine how many satellites are on the Earth or on your head. And OneWeb or Telesat, Amazon also, they are on the race of installing the LEO satellite, right? But satellite, the Starlink are the first move. So now it's already 2 years ago, like August in 2022. The Starlink CEO, the Elon Musk, and the CEO of the T-Mobile, they show up the satellite meet the cellular. So and with the unmodified T-Mobile, the cell phone, the Starlink service can be used. So with your phone, with your cell phone, you can also connect like Starlink service to kind of avoid the dead zone problem, right? So this is very surprising thing, and this year, actually, the January 2024, they launched these services. I mean, the satellite for the direct to the cell. So they launched a 6 LEO satellite for these services. So it's work with the existing LTE phone wherever you can see the sky, right? So no change for the hardware or firmware or special application are required. Just use if you are outside of the T-Mobile coverage, you can connect the Starlink satellite. So now they provide a text short text message, but they will provide some voice and data service in from the next year. Also, they plan to connect IoT services with the common LTE standard and within the 1 year. So this is a very kind of the groundbreaking technology, because it used to require some kind of dedicated gate, kind of the small dedicated VSAT terminal to use Starlink service. But now it turns out to be no dedicated or new hardware are required for the satellite services. Just with your cell phone, you can connect to this Starlink service. So that's a very groundbreaking story, right? And 3GPP also tried to work on standard of the non-terrestrial network, so with emphasis on LEO satellite. So this is kind of the plan for the NTN, the standardizations. So now they're in almost end of the release 19, and now they are moving to the release 20. So even in the release 17, they already standardized some kind of the key feature of the NTN services. But now they are making more the NTN standard more advanced. And then, so now they're pushing more as NTN standard are more harmonized with existing terrestrial network, right? Because the NTN standard are to support the satellite network, and already 4G and 5G terrestrial network are well defined. So for the 6G, of course, we have to think about how to harmonize those two different networks, satellite and terrestrial network, right? So many companies are pushing this direction to their the standardization strategy. Okay? Right. So yeah. So let's move on to the technical challenge of the satellite communications. So the key feature of satellite communication is twofold. The first one would be the multicast transmission. So this may be changed in the future, but if you look at modern standard of satellite communication called DVB-S2X, the transmission based on the frame-based pre-coding, right? So long code words are adopted to cope with large fading loss by multiplexing the data of the multi-users belong to the same beam. So it can also increase encapsulation efficiency, and the same data is decoded by the group of users. So this is about a multicast transmission. And also, another key feature is multi-beam transmission, as I mentioned before. So effectively, what the system looks like is multi-group multicast or multi-beam multicast. Each group here represents one beam here. So in typical, the terrestrial network is about the multiple unicast transmission, but now the satellite system can be modeled as multi-group multicast transmission. So here are some key challenges. So it needs to interbeam interference, right? Because it's a very the user overloaded system. So where a total number of users is much larger than number of the antennas here. So in the satellite communication industry, they call the antenna as the feed. So you can imagine how many the supporting users on the ground. I mean, of course, the number of users should be much larger than number of antennas at the satellite communication system. And also, the high propagation delay would be very problematic. In GEO system, it takes a 250 milliseconds for the one way trip. So for the round trip, it's about 500 milliseconds should be required. But LEO satellite still it's required like 20 to 25 milliseconds. So it's very high propagation delay. So it's hard to get accurate channel feedback in a Korean time, right? So why is that? Because it's also when it comes to the channel feedback, it also takes a lot of time. So when the channel state information is fed back to the satellite, it's already outdated. It's already stale information, right? And also channel itself is very fast, rapidly changing because due to the fast move of the LEO satellite, right? So it's very hard to predict their channel information for the interference management. So imperfect channel state information and transmitter is very the serious problem in LEO satellite cases. Okay. So let's move on to discussion on why the existing beamforming or multiple accesses is not enough to handle these challenges. The first one would be interbeam interference might be very severe due to the overloaded scenario. So yeah, as I mentioned earlier, overloaded scenario is number of user is much larger than number of antennas at transmitter side, right? In typical terrestrial network system, number of users are quite similar to number of user. So when they have to support more the user, then the base station usually select the user, like with some scheduling, right? Scheduling policy. So they just select the partial set of the user. But in the satellite communication, we cannot do kind of scheduling like that because why they use a satellite because of the continuous coverage. So they have to support the user at the same time, right? And so knowledge of the channel state information of satellite link should be depending on what type of satellite you use. If you have a GEO satellite, there is a very long latency to feedback any CSI. But on the other hand, GEO satellite is very stationary, so the CSI is not changing that quickly. But if you take the LEO satellite into account, your feedback delay is not that long, but the channel itself is varying pretty fast, right? To tackle this challenge, we have to come up with some robust and flexible multiple access based on rate splitting multiple access, the RSMA. Okay. So now let's move on some robust multi-beam design for satellite communication. So before we move on, maybe if you have any question, feel free to ask anything. Otherwise, I can, yeah.
I've got a question.
Oh, sure. Go ahead. Yeah.
Okay. Now for the LEO, say 7,500 kilometer per second.
Mhm.
Will OTFS not help us solve the problem? Orthogonal OTFS modulation technique.
Oh, yeah, OTFS, yeah. So you are talking about the OTF system, right?
Yes, using OTFS to solve
Yeah.
the problem.
So yeah, so as you know, the OFDM system, the orthogonal frequency division multiplexers are very sensitive to the frequency synchronization issue, right?
Yeah.
So the overflow effect make some frequency synchronization issue. So some people claims that the OFDM is not very effective for the NTN system due to the large amount of Doppler. But OTFS also are very effective for not only the high Doppler effect, also it's very effective for the high Doppler range. So what I mean is, in the satellite communication system, although it's provide, I mean, it's the channel has a lot of very huge Doppler effect, but it's a line of sight dominant one, line of sight dominant channel, right? So in that cases, OTFS might not be very effective because if the channel is ROS dominant, then maybe pre-Doppler compensations or post-Doppler compensation might be also effective. So, but it has a lot of issue. I mean, OTF is very effective or not in the case of LEO satellite. But yeah, OTFS can be also applied for the multiple access for the LEO satellites communication system too. Yeah. So yeah. So anyway, so we have to also develop some new multiple access for LEO satellite communication system with a Doppler effect, very high Doppler effect. But we also have to think about our satellite channel is quite the line of sight dominant channel. So we can also handle like pre-Doppler compensation also, not only the OTF, FS. Okay. All right. So I hope that answered to your question. And
yes.
Thank you. So now let's move on to robust multi-beam design for satellite communication. So this is joint work with Imperial College London and Seoul National University. So before going to that, let's review the fundamentals of the RSMA, the rate split multiplexer, which is our building block. So this is an architecture of the architecture of transmitter for the K-user rate splitting multiplexers. So what do we at the transmitter is to split the message we want to transmit to each user into two parts, the private and common, right? So the first message is also split into the private and common, and the kth user message also split into two parts, the private and common. Yeah. So a group of the common message want to be decoded at the all users. So making those group of the message are into the common message, right? So, but note that here, the common stream is decoded by all user, but it's not necessarily intended for the all user. So why we split our message in two parts is for the better or efficient interference management, right? So we send K private stream along with the common stream. Also, we can design some kind of linear precoder for each stream, private and common stream, like this. So this is how the RSMA can send the message. So let's see the relationship between RSMA and other multiplexes by looking at a two-user example in order to understanding the basic building block. So key difference between RSMA and normal and SDMA is how the messages are split. So for RSMA, as I mentioned earlier, each user message, so let's just assume that there are two users here. So each user message is split into two parts, and common and private, and common and private, right? But if you look at the NOMA, so also we assume that a user one has a stronger channel. So in this case is user one's message are for the just common message, because user two can also I think I explained it in the other way. So user two message is a common message, right? Because the user one can decode it other user message in normal setting. So here, if you look at this figure, user two, the word channel user message is just allocated to the common message. So no private for the word channel message, and the user one message is just treating the private message like this. Because the weak user's message is allocated the common message, so that its message are decoded by the both user. So that's the theory behind NOMA. And SDMA, on the other hand, the both user message are transmitted as a private message. There's no any information into the common stream in this case. So any of the message are treated as a noise in the non-intended user, right? That's the SDMA we use for the 4G and 5G, right? So in essence, by adjusting how much we put into the common and private, the rate splitting boils down to normal and SDMA, as well as multicasting or the OMA. So this leads us to conclude that RSMA can be the most generalized multiplexer scheme. So as for the receiver operation of the RSMA, the both user first decoded the common message by treating private signal as noise, and both users perform successive interference cancellation and retrieve each private message by treating other users' private signal as a noise. Okay, so we can say that RSMA can partially decode interference and partially treating interference noise. So here, NOMA is just fully decoding the interference, and SDMA is the fully interference as noise. So that's a two extreme cases. But RSMA, they bridge the two extreme cases. So it's partially decode interference and partially treat interference as noise. So that's a motivation why we can consider RSMA is the most generalized scheme. So another motivation of RSMA is promising MIMO solution with imperfect CSAT cases, apart from generality of the message setting. So last 10 years, so most of the information theory limits for the MIMO cases are discovered, but we cannot guarantee any optimality in case of imperfect CSI setting, right? So in conventional approaches, we try to optimize robust precoder optimization for private message setting with imperfect CSIT. However, the RSMA turns out to be optimal in degree of freedom sense with imperfect CSIT. So it's precoder design not only for private message, but also the common message here. So this is a new approach for the RSMA, right? So this is a degree of freedom region with the imperfect CSIT cases for the two-user cases, right? So the blue curve here is the degree of freedom region by rate split. And So the green curve are just the existing method, right? And dotted line can be achieved by the TDMA, the time division multiple access. So you can recognize that RSMA can achieve the most larger degree of freedom region, but also not only it achieving the better result, also in the literature, RSMA turns out to be the optimal degree of freedom achieving scheme. So you cannot achieve the better than this, the blue curve, right? So it's already has a very solid foundation of the theoretical foundation in case of the imperfect CSIT. Although it's the metric is a degree of freedom region, it's effective for the highest, very highest in our setting. So this is an illustration of the where the robustness RSMA come from. So if the so here so this is an imperfect CSIT channel model. So the real channel is the sum of estimate channel and the error vector, right? So error can be also modeled as like this: the transmit power to the minus alpha. The alpha is related to the number of feedback bits, right? So if you increase the feedback bit according to like transmission power, then you don't have any problem. I mean, in terms of interference management. But I mean, like a 405 system, your feedback bit is not increased according to your SNR, right? So your degree of freedom is not very perfect when it comes to limited feedback system. Okay. So we decompose into the superposition of two networks with a perfect CSIT and no perfect CSIT here. So it turns out to be it has a very big capacity gain by increasing the degree of freedom gain by the RSMA, right? So far, we've looked at only degree of freedom gain of RSMA or for the very high SNR cases. But when it comes to the sum rate performance metric, also it has some gain. So red one is for the RSMA, and blue cover is based on Jefferson or the STMA cases. So as you can see, according to the different number of users and number of antennas, the RSMA has the benefit over the existing the STMA cases. Also, when it comes to limited feedback cases, the rate splitting has the best performance gain here, right? So green one is the single user and multi-user transmissions, and here the red curve are based on STMA, the Jefferson beamforming. And this pink one is by the TDMA cases, right? So when it comes to the TDMA cases, you just split your resources you have into the small piece of the resources, so to avoid some inter-user interference. But because too inefficient of your resources, so it has the worst performance compared to the rate splitting multiple access. So in conclusion, the RSMA can achieve the higher sum rate while reducing the feedback. Okay. All right, so let's see how we can apply RSMA in the context of satellite communication. As I mentioned earlier, RSMA is very powerful and generalized multiple access scheme in case of the imperfect CSA setting, right? But as I mentioned earlier, LEO satellite communications are in the case of the imperfect CSI setting because of fast movement of the satellite and also very long feedback delay, right? So this is the channel model of the multi-beam. So this is time-varying equivalent channel vector between satellite and user, ith user, right? So it composed of the different. So this is a Hadamard product, and so it's a product of the 4 different terms. The first one would be time-varying rain attenuation between satellite antenna and ith user, and C is deterministic link budget parameter. So this is more like including the path loss and so on. And B here is antenna gain for the beam I. And theta I is the vector of phase component of the channels, including phase noise introduced by the local oscillator. So let's elaborate the term one by one. So here is assumption rain attenuation. So it's modeled by the log normal distribution, right? So so take a log here. That's the random variable is followed by the Gaussian distribution here. And this is a deterministic link budget, right? So it's also a matter of the frequencies and also the receive antenna gain and noise power at the receiver side. So with the which kind of the antenna you use or frequency use, so this link budget parameter should be set up. This is the beam gain. So beam gain is modeled by the relative position with respect to the beam center. So if user are very far from the beam center, your beam gain is very small. But if the user are very close to the beam center, then the beam gain should be very high value. So it should be depending on the angle of users and the beam center here. So that's a phi. So if your phi is small, then your beam gain is very high. If your phi is large, then your beam gain should be decreased. So here is some system model for the first work on RSMA-based multi-beam satellite channel. So consider the K user served by the M multicast satellite beam. So as I mentioned earlier, due to the frame-based precoder of satellite communication, message of the user in each group or beam would be encoded into the single code word and transmit over the air. Okay? So here, so there are 2 different, the symbol here. The first one is common and the other one is private. Okay? So private message here S1 refer to the multicast message for beam 1 by encoding all user message in the group 1 into this single code word. And in the meantime, the partial of the multicast message can transmit by the part of the common message SC here. So here, instead of transmitting M beam, M plus 1 beam are transmitted over the air. To do so, we have to define the rate of the beam, rate of the mth beam, which is sum of the private part and the common part, like this. Okay. So what we have to do here to optimize precoder design, it's a private and then the common precoder design, including the power, right? So here is our optimization problem. This is an optimization problem they want to look at. So they tackle maximum fairness maximization. So this is a rate for the mth beam, right? So instead of this, to maximize some rate maximization or so on, so they tackle maximum fairness. the maximize of the mean of the beam's rate, right? So this is a constraint for the common message rate allocations, and those are a perfect power constraint or individual power antenna constraint. So people in satellite communication are very cautious about the efficient use of power. So they don't play with a total power constraint as in terrestrial network, but rather per antenna constraint here, like this. This is non-negative rate constraint, right? So this is this is an optimization problem in they want to look at. So so I don't want to go into details about their solution, but they tackle this problem based on a sample average approximation and WMMSA solution, which is very very well known in the MIMO multi-user the beamforming technique. So I don't want to go into details, but let's just see the simulation result. So here we have the 7 beams here, 7 beams and 14 users. So 2 users per beam can be allocated. So it's quite uniformly distributed. So here there is a RS, which is marked on the red, and no RS is the blue curve here, right? So no RS refers to the very classical multi-user linear precorder, right? So there is no split of the message. So you see that here, for instance, the perfect CSIT, the solid line here, okay? The blue one in the multi-user precorder and the red one in the rate split multi-box, it has a lot of gap between those two curves, right? The split of the message here enable you to manage interference between all beams much more effectively. So also when it comes to imperfect CSIT, also the rate splitting perform better compared to the classical linear precorder message, right? And also if you look at the effect of CSIT imperfection, as you go on an axis on the left to right, you actually degrade the quality of the CSI, right? And what you see here, the quality of CSI degrade the gain of the RSMA over no RSA. The no RSMA is relatively increasing. So you have to focus on the gap between the red curve and the blue curve here. So this is because of robustness of the RSMA in the presence of imperfect CSIT. And here there is another example. So the loss incurred by the per antenna power constraint is quite marginal here. So that's not a very significant issue. So if we got to the hotspot scenario, so what's the difference between hotspot and uniformly distributed scenario? For example, in this cases, in the previous cases, also the 7 beams and 40 user, but in each beam, 2 users are located. But in this cases, like a 1 beam, the 1 beam includes 8 users, and the other remaining beams support only 1 user. So this is quite the user distribution is not quite even, right? So this case is called the hotspot scenario. So in this cases, RSMA can even perform better than no RSA cases. So the gain become more visible here, right? Yeah, so this leads to actually the complete imbalance between the rate in one beam and versus rate in other beam. So those are quite interesting simulation result. So next scenario is when you have an integrated satellite and terrestrial network. So from the satellite, the multi-beam multicast transmission are done, and in each beam, because as you can imagine, the coverage of the satellite are very huge. So in each, even within a very spot beam, also it might have some terrestrial network here, right? So within a coverage of the area of a satellite beam, you may have also terrestrial network, right? So some users are here served by terrestrial base station, and other user outside of this coverage is served by the satellite. Okay, so those users in this terrestrial coverage are supported by this terrestrial base station, and one in outside of this coverage is support from the satellite. So that's our assumption. So we can think of two different architecture to efficient manage of interference, right? The first one would be the coordinated scheme. I mean, in between satellite and terrestrial network. So in this case, there is no data sharing between terrestrial and satellite system, right? Only the channel state informations can be shared between satellite and terrestrial network, right? But when it comes to cooperative scenario, then both CSI and data information at the gateway for a satellite terrestrial network should be shared. Of course, it requires much more kind of overload, control overhead, but it might provide the benefit and performance gain, right? So there are always a trade-off between the performance gain and overhead, right? But our focus is the coordinate system. So without data sharing, we can do better. Even in the absence of the imperfect, even the absence of the perfect CSIT, we can handle the inter-satellite and terrestrial network interference. So, our focus is to how to manage interference in and between the both satellite and terrestrial subnetwork without data sharing, which is the coordinated scenario. And we'd like to find optimal resource allocation to mitigate interference by the race multiplexes. Okay. So as I mentioned earlier, there are multi-beam structure. Multi-beams are supported by the satellite. In each beam, there are some terrestrial network here. Okay? But if they share the frequency reuse, it's caused a lot of the interference issue here in between satellite and terrestrial network. Okay? So ray splitting comes into play for this efficient interference management. So each satellite will perform its own ray splitting group multicast scenario to handle inter-beam interference here. But on the other hand, terrestrial base station also perform another ray splitting here for multiple unicast scenario to mitigate inter-user interference, right? So here is our observation. So no interference link between terrestrial base station and user link. So why is that? So what is the motivation for the satellite user? Because it's lack of the terrestrial network coverage, right? If they can connect, they have some connection to the terrestrial base station. Why are they connect to satellite? Yeah. So we can naturally assume that there is no strong link from terrestrial base station to satellite user, right? So this is like a kind of the Z channel because there is no link between terrestrial base station and the satellite user. So very strong interference should be considered from satellite to terrestrial user. So that's a problematic, the link, interference link. Okay. So different from the rate splitting, the Han-Kobayashi scheme, I don't know how much you have some knowledge about information, network information theory, but Han-Kobayashi scheme strategy for the interference channel is very well known. The strategy for the two-user interference channel, like this, so without data sharing. Okay? So its transmitter split its message in two parts, also here, the common and private. So both common message should be decoded by the old receiver here. Okay. So this is a very well-known kind of interference channel transmission approaches. So by adjusting power located common part such that multiple user interference is within a noise level. So that's how the Han-Kobayashi scheme, the design, the split the message, right? So private power set to that interference is received as noise level at the non-intended receiver. So yeah, so in theory, if your interference is very weak, then optimal strategy is treating interference as noise. So if your interference is very strong, then optimal strategy is just trying to decode their interference and successive interference cancellation and subtract it and try to decode its own desired signal. So for the two extreme cases, we already know exactly optimal the scheme. The problem is in between, so like a medium interference cases. So in this cases, Han-Kobayashi scheme can provide some kind of the suboptimal manner, but it turns out to be it's very close to the optimal. In information theory, it can Han-Kobayashi scheme can achieve the capacity within a 1 bit. So it has a very good information theory foundation. So with this, we exploit Han-Kobayashi. We actually try to combine Han-Kobayashi scheme and array splitting by adjusting allocate to the super common. So we kind of come up with a new kind of message called the super common message to handle the inter-satellite and terrestrial user, the link here, such that network interference between satellite and terrestrial is within noise level after the successive interference cancellation. So that's our kind of novelty of our kind of new development. So super common message can effectively handle inter-network interference here. So on top of that, we can also handle inter-beam interference as well as inter-user interference within a terrestrial network. So that's our proposed multi-beam array splitting structure. And those are the design for satellite transmission. Yeah, for the satellite transmission, not only for private message and the common message, also it has to transmit super common message so that inter-system interference between satellite and terrestrial users should be handled here, the super common message here. So those are the received signal at the satellite users. So there is no interference from terrestrial base station. But on the other hand, this is a transmission model by a terrestrial base station here. So it transmits the common signal and private signal, right? So those are the received signal at the cellular user or the terrestrial user here. So this terrestrial user experience the severe interference for satellite. Not only for satellite, also there it's experience inter-user interference between between the terrestrial user too. It experience a lot of the interference issue here. So those are the rate of the super common message and common message and so on. So we can define based on the information theory foundations, and we can define some SINR and rate for its corresponding the message. Okay. So those are also the private stream SINR and rate expressions. So yeah, I'm not going to details of the how we can define this rate constraint, but I'd like to explain some of our optimization problem setting. So we want to maximize the mean rate of the all user, including satellite and terrestrial user, right? This is for the terrestrial users, and this is for the rate for the satellite user. So min max problem to tackle the user fairness problem. Okay, but the problem is formulated as non-convex problem because of the rate, constraint involved with non-convexity. So where the global optimal solution is challenging to obtain. So the efficient solution can be obtained by employing the kind of successive convex approximation technique to reduce the complexity of and make some problem more tractable, right? So we use several techniques, including FGF form and introducing the slack variable or the rate expressions to tackle this non-convexity. I'm not going to details of this technique. Convex optimization technique, but we use several kind of technique. For the successive convex approximation, SCA, and so on. And also to avoid some low constraint, also we use some kind of second order cone program, like SOC. Yeah. So if you're interested, you can also take a look at this paper. So this paper is already accepted to the TVT, the IEEE Transactional Vehicle Technology. So if you're interested, please take a look at this reference paper. So finally, we make our problem into equivalent kind of convex problem. Not exactly, this is more like it. So we try to solve our problem in an iterative manner with the CVX tool. So this is a numerical result that confirms significant performance gain, right? So this is a min-max. The MMF is min-max, the fairness. So this is the rate, the BPS per hertz. Spectral efficiency. So we kind of the altitude of the satellite here. So by doing so, we can change the level of interference. Why is that? Because if the satellite increases altitude, then interference towards the terrestrial network is very marginal, right? Because it's very far from the ground. But if your satellite going down, so altitude of satellite is very little, like a 500 kilometer in the area of the LEO satellite, then it's provide very harmful interference, right? So that's a geometry of this the x-axis. So there are some existing work, some SDMA and RSMA and SDMA, ISN. So So this green curve are SDMA. I mean, the performance given by the classical multi-user precoder. And also OMA means that orthogonal multiplexes. So satellite and terrestrial, they don't share the frequency. So they divided the whole resource in two parts, one for terrestrial, one for satellite communication. So it's provide very inefficient of the wireless resource exploitation. So that's provide the worst performance. And RSMA OMA, that's a better, but still not good. And this red curve are ISTN. So they share the satellite, I mean, the frequency between the satellite and terrestrial, but the precoder design is based on SDMA. So it doesn't have a very good performance, especially for the altitude of satellite is very, very low, where interference to the from satellite toward the terrestrial user is very strong. The performance has some saturation because as the satellite it's getting closer to the satellite user, of course SINI should be increased. But in the meantime, also it provides a stronger interference, so it doesn't have a good kind of rate improvement. But the family of the RSMA ISTN, so it provides a better performance as the altitude of satellite decrease. So this is also very very recent, not our paper, but it's the paper written by the Imperial College London Bruno Klotz group. But it does not actually very carefully handle the inter-satellite and terrestrial network interference here. So the blue one is our proposed one performance. So it provides a better than even a very recent RSMA scheme, right? Especially in case of a low, in case of the LEO satellite setting, where more interference toward terrestrial user exists, right? So with this, yeah, we can figure out more performance gain when altitude of satellite is very low, right? And also, if we don't use RSMA, the rate performance quickly saturate as the altitude decrease, right? So that's a performance gain. And also, as number of users in each beam increase, the rate performance decrease due to the multicast traffic. Because if the multi-user, if the multicast transmission rate is defined at the minimum of the user in each beam, so as the number of users in each beam increase, of course, the rate decrease here. But still, our proposed one provide the best performance compared to other recent proposed RSMA and the STMA-based ISTN. And also, regardless of imperfect CSIT or the CSIT error model, the level of CSIT error. So our proposed one performed the best, compared to other existing benchmark scheme. So proposed multi-beam RSMA outperform existing beamforming technique regardless of the CSI data. Right now, I want to discuss some possible object function of the satellite communication. So, of course, you can consider some rate maximization as in conventional, like a multi-user MIMO setting in terrestrial network, right? But solution might not be very proper in terms of coverage extension, because if you try to maximize some rate, maybe you give up the user with a very poor channel, right? So that's always happening in the water filling solution, right? So this solution might not be very proper in satellite setting. So yeah, I mean, if you consider role of the satellite communications, coverage extension should be the most important role, right? So as in our work, as I explained, max-min fairness would be also very interesting. Also, it's a fulfill the coverage extension role, right? But also important objective function would be kind of service flexibility to satisfy heterogeneous demand over time or geographical region would be required. So traffic-aware rate maximizations or rate matching problem would be very interesting. So maybe I can explain the rate matching. So for example, if your beam is very large, maybe this is we can think of like a one spot beam coverage is like a several hundred. So this is the user in India, and this is one in the user in the Korea, and those are one user in the Japan, and this one user in like China. But they have a different time zone, right? So they have a different kind of the service requirement according to different time zone. Of course, also the service kind of the data requirement are also based on their geographical region, but also that data requirement or QS requirement also depending on their time zone, right? So their requirement should be vary according to different the beam, right? So here our K hat means that kth beam requirement. So the first beam require like 1 giga BPS, and second beam require like 20 giga BPS, and third beam require like 100 kilo BPS or so on. So satellite usually has a power limited system because it doesn't have some power source. Only it's depending on the solar power. So it has a very the strict limitation of the power. So with a very limited power, how they can allocate their power? So the rate matching problem would be very very good kind of objective with a limited power, right? So how to match with their user requirement or beam requirement? So that's so this is I actually suggest for the design of satellite communications, because by considering the situation of the satellite setting, right? So we have several paper already published in some IEEE magazine article to tackle the rate matching problem. Okay. Yeah. So those are some the example of the diverse or uneven traffic demand. So in this example, in some reason it requires very small amount of the traffic demand, but in some reason it's very high the traffic demand. So with very flexible service demand, we can design the beam power allocation or beam form. So that's the new kind of object function we can think of. Okay, so and also before actually conclude talk, I'd like to advertise some event and I'm organizing. So actually this is already gone. Already finished. So this is last WCNC, the 2023. So we gave a tutorial on Internet of Space Things with my colleague. So I heard that Aryan already gave a talk in this lecture series. Also, he is one of my close friend and a colleague who work on this NTN field. So yeah, we gave a talk on how we can design this NTN with emphasis on Internet of Space Things. And also last GlobeCom conference, which is a flex conference in Communication Society, we also gave a talk on. We gave a tutorial on non-terrestrial network for next generation global connectivity. Yeah, which held in Kuala Lumpur in Malaysia. Also, after finishing this GlobeCom conference, tutorial, also Aryan and I also make some short video clip on what kind of topic we are discussing in tutorial. So in YouTube, you can also find the very short video on this. And also regarding the rate split multiple access, I also read IEEE Communication Society, the special interest group on RSMA. So I'm serving a vice chair of this special interest group. So if you're interested, you can visit this website. So there are lots of the tutorial and also the lecture series on RSMA. Including myself. There are some very interesting talk and magazine article has been available in that website. So yeah, please visit this website if you're interested. Okay. So I think that's all. So today I cover the motivation of the satellite communication for 6G and the key challenge of the satellite communication. So what I developed for the NTN for 6G is the robust and flexible beamforming design for satellite communication. That's I think the most important the challenge for the 6G NTN scenario, right? So I think that's it. So thank you for your attention and thank you for listening. So if you have any question, feel free to ask anything.
Yeah, I must say that how precise you are. It is exactly 3:30 here.
Yeah.
So I should add on one more thing. All your slides were self-explanatory and you have described them all in a very wonderful way. Still, if you have any query, the room is open for any query. If any participant is having any query. Yeah, there seems no question here. So already we have recorded your session. And regarding that, the YouTube video, the conversation between you and Dr. Aryan, I have seen that. that video. Yeah. I always follow you. Yeah. So I think we have some queries. Yeah, please put your query. Yeah, believe.
Okay. Professor Shin, in course of your presentation, I noticed you didn't talk about power in required to do the transmission, which is something I'm thinking in my head, because I know the more power we use, it may also cause interference or increase interference in the system. So what's the role of power in your analysis? Yeah.
Okay, I think I didn't get your point. So what was the question?
No, I'm saying in all the equations, signal to noise ratio I saw, I didn't see any component for power. So I know you said the LEO satellites will need less power. They use less power than to transmit to to the users or the user equipment, but I didn't see the component of power in your analysis. Yeah.
Oh, I see. So, yeah, I mean, okay, maybe I think, yeah. So, in a SINI expression, yeah, actually, yeah, maybe we can see the SINI expression. Yeah. Yeah, exactly. I think you have a very good question. So actually the W here is a precoder, but W incorporate the power actually.
Okay.
Yeah. So it doesn't have a unit power. So it has some its own power. So, but there are some freedom of the power location between the private and then the common and so on. Yeah.
Okay.
So it's as you mentioned, the power is not explicitly shown in the SIN expression. Yeah. It's a matter of the optimization variable.
Okay. And then slide 28. In
28.
slide 28, yes. If you go to slide.
Oh, 28.
Now, in this simulation, we just said M is